Today we'll think about the last two new topics from Chapter 14, damping. We've thought about that a little already, and then resonance. Resonance is actually a very important topic when we get into waves. So here's our simple model for any oscillating system, mass attached to a spring, and the mass can oscillate back and forth horizontally. Let's consider what happens when this mass is in the middle of its oscillations, and we start watching it when the mass is right here at equilibrium, but in the process of moving left to right. So velocity in that direction, and let's say there is a friction force from this surface acting on the mass. Since the mass is sliding across the surface, the particular type of friction force is kinetic friction, which I indicate right there. And remember, kinetic friction always points opposite to the velocity. So the mass is moving to the right, so kinetic friction points to the left. And we know how this works. When the mass is moving away from equilibrium, it's always slowing down because the restoring force will be pulling backwards on it. It slows down until eventually it comes to a stop, and that's as far as it goes on the right-hand side. And by the time it comes to a stop, it's gone through a displacement that we'll call delta x meters, and that's the final moment of the process that we'll be thinking about here. The friction force does work on that mass. Work happens when a force is applied to a moving object, like the friction force, kinetic friction applied to the moving mass here. And it's by means of work that energy is given to an object or taken away from an object. And the numerical value of work tells us how much energy gets moved around, and the sign of the work tells us whether the energy is given to or taken away from the thing that's having work done to it, the mass in this case. So here's our general rule from last semester for the value of work. The magnitude of the force that's doing the work times the magnitude of the displacement times cosine of an angle, that angle being the angle between the displacement direction and the force direction. So what have we got in this particular case? Well, the work done by friction is just the magnitude of the friction force times the magnitude of the displacement times cosine of the angle between displacement and friction. Well, the mass is moving to the right. It has a displacement to the right, but friction always points opposite to the motion, so the friction points to the left. So the angle between the displacement direction and the force direction is 180 degrees. So the last term there in the work equation is cosine of 180 degrees. Trigonometry tells us that cosine of 180 degrees is -1. So that results in a negative work done by friction on the mass. Energy is taken away from that moving mass. Remember, we think of the total energy in these oscillating systems as just kinetic energy plus the elastic potential energy plus thermal energy. We define another type of energy, mechanical energy, which is just the sum of kinetic plus potential. So the total energy in this case is just mechanical plus thermal energy. And what that friction force actually does is take away mechanical energy. When the negative work is done on the mass, energy is taken away from the mass. Specifically, mechanical energy is taken away. That is, there's a negative change, a decrease in the mechanical energy of the system, And that energy doesn't just disappear, it goes somewhere. It goes into thermal energy, right? The work done moves mechanical energy into thermal energy. Thermal energy being basically the mechanical energy of the molecules that constitute the objects in this system. So an increase in thermal energy, like we've said before, whenever there's friction, thermal energy is increased. Now this is to use the technical term, this is an irreversible process. Once that energy is taken away from the mechanical energy and put into the in the form of thermal energy, it can't be extracted from the thermal energy and given back to mechanical energy. It's the energy taken away and put into thermal energy is totally lost to the mechanical energy. The mechanical energy cannot get it back. Now, mechanical energy decreasing. Well, there's one clear visual manifestation of that in any oscillating system. We've seen before that the mechanical energy of an oscillating system is directly proportional to the square of the amplitude. So, of course, if the mechanical energy is decreasing, that is, if there's a negative change in the mechanical energy, that means we will see that mechanical energy is decreasing because we will see that the amplitude is decreasing. A negative change in the amplitude. So how would that look on a graph of the position versus time for an oscillating object if the amplitude is decreasing as time goes by? Position, time, and let's imagine that we start the oscillation by pulling that mass away from equilibrium in the positive direction, and then at time zero we let go. So at time zero it has a positive displacement away from equilibrium, and then it starts oscillating. But friction is taking away mechanical energy, and we will see that happening because we will see amplitude decreasing. Something like that. Every half cycle, the maximum displacement away from equilibrium is smaller than it was a half cycle before. Amplitude is decreasing. If you drew what the book calls an envelope, just a curve that connects all of the points of maximum displacement away from equilibrium, that curve turns out to be an exponential function. An exponential change is something that happens a lot in all kinds of different situations in nature. So it's worth thinking about a little bit. Over the last year, we've been trying to deal with one example of exponential change, that the spread of a communicable disease. In that case, the number of cases will increase exponentially if if the population is doing nothing about it and just allowing it to spread naturally. And in some parts of the country, have been almost in that awful state, and much less so, fortunately, here in Ohio. Anyway, exponential decrease. The exponential function, amplitude as an exponential function of time, looks like this. The amplitude at any particular time equals the amplitude right at the start, the amplitude at time 0, right? That value of position is A0 times the exponential e to the minus time over tau. Tau is a length of time called the time constant, and as described in the book, it's a good way of indicating how strong the damping is or how weak the damping is, how quickly the amplitude would fade away, or in a strong damping condition or strong friction, or how slowly the amplitude would fade away in a so-called weak damping situation, weak friction. Let's think about what would happen to these numbers if the damping got stronger, the friction force got stronger. Strong damping, or stronger friction force, which we would call stronger damping, corresponds to a smaller value of tau. And we'll see why in just a minute, but just let's work through the algebra here. Smaller tau means that this quotient up here in the exponent, t over tau, is getting larger. So let's rewrite that function. A0 e to the minus time over tau is really the same as A0 over e to the plus time over tau. So if t over tau is getting larger, then e to t over tau is getting larger. E is any number to an exponent where the exponent is increasing, well, that number gets larger. Which means the denominator of this fraction is getting larger, so the fraction itself is getting smaller. That is, amplitude is getting smaller. In other words, for strong damping, which is indicated by small values of tau, stronger damping, which is indicated by smaller and smaller values of tau, that results in smaller and smaller values of amplitude for any time you might choose. Well, if at any particular time the amplitude is smaller than it would have been at that time, it got smaller because the damping was stronger. It got smaller faster because the damping was stronger. The friction force was stronger. Regardless of what the value of time is, this number is always smaller if tau is smaller in the strong damping situation. Now, let's think about, well, tau is a length of time. Exactly how much time is it? Let's look at our exponential function for amplitude at time tau, when t is equal to tau. then you've got original amplitude e to the minus t, which is tau in this case, over tau. In other words, a to the times e to the minus 1, or original amplitude over e. Ask your calculators to do that to find out what the value of 1 over e is, and you'll find that this comes out to about 0.37 A0. In other words, after tau seconds have elapsed, the amplitude is down to just 37%, or roughly 1/3, of what it had been at the start. Or, to put it another way, every tau seconds, the amplitude ends up only 37% as large as it was tau seconds previously. Now let's think about how we can use this equation in calculating situations. And for that, we have to think about another kind of function that's very closely related to this exponential function. Let's say y equals e to the x, just the simplest form for the exponential function. That statement is equivalent to another statement that involves another function, the function called the natural logarithm, indicated by ln. These two statements, when you put them together, sort of tell you what the definition of this logarithm function is. The slogan to remember, we'll come back to logarithms again when we think about sound and sound intensity, and the intensity of the energy carried by waves. A logarithm is an exponent. Repeat that to yourself until it becomes second nature. That's the first thing you need to think of when you hear the word logarithm. A logarithm is an exponent. What kind of exponent? Well, the logarithm of this number, and x is just a name for that logarithm. Since logarithm is an exponent, x is the name of that exponent. The logarithm of y, also known as x, is the power to which you raise e in order to get whatever is here in this slot of the natural log function. Like that. For example, let's say, what is the natural log of 1? Well, the natural log of 1, which we're calling x, is the power to which you raise e in order to get this number. And remember what you know about exponents. Anything to the 0 power equals 1. The natural log of 1 is 0. And there's one more simple example. What's the natural log of e? Well, natural log of e, which also goes by the name x, is the power to which you raise e in order to get whatever is in this slot. So obviously in this case, X is 1. The natural log of E is 1. Okay, now we'll see how we can actually use this pair of ideas to answer questions, figure out numbers. Let's say there's some kind of a damped oscillation such that after 60 seconds, after 1 minute, the amplitude has decreased by 10%. The amplitude is now just 90% of what it had started out as. In other words, the amplitude at time of 60 seconds is 90%, 9/10 of what it had been at the start. And that's enough information to figure out what the time constant is in that particular case. And to do that, and the first step is just to write out the basic exponential function of amplitude and insert as many quantities as we know. So amplitude after 1 minute, 60 seconds, is 0.9 times the original amplitude, but amplitude as a function of time is A0 e to the minus time over tau, and in this case the time is 60 seconds. We're solving for tau, which means we need to get that tau out of the exponent if we're going to have any hope of actually doing algebra to solve for tau. But we can use the relationship between exponentials and natural logs to do that, to get it out of the exponent. If it is the case that y equals e to the x, then natural log of y is just plain x. So let's make this a little simpler by canceling out the a zeros on both sides of the equation, and then we're left with 9/10 equals e to the minus 60 seconds over tau. Compare that with the basic form. Y is e to the x. Y corresponds to 0.9 and x corresponds to minus 60 seconds over tau. So if we then say that natural log of y equals x, y corresponded to 9/10. X corresponds to the exponent, minus 60 seconds over tau. Don't throw away that minus sign, that actually matters. So tau, the time constant in this case, is actually minus 60 seconds divided by the natural log of 0.9. Well, it turns out that for any number less than 1, its natural log is negative. So ln of 0.9 is negative, and so a negative number in both numerator and denominator. That means the fraction is positive, which is just what it has to be, because this is a length of time, which is length of time is necessarily a positive number. And when you do the math and have your calculator work it out, it comes out to about 570 seconds, which is about 9.5 minutes. So in other words, in this oscillating system, if you let it go for 9.5 minutes, the amplitude will have decreased down to just 37% of what the original amplitude had been after 9.5 minutes, roughly, the amplitude is roughly 1/3 of what it had been at the start. It's lost a lot of mechanical energy in that time. Let's try one more example. In this case, let's say we know the time constant. We know we have enough information about the forces in the system to figure out the time constant, and we want to know how long it's going to take for that system to decay away, for the amplitude to decrease by any particular amount. So let's say in this case we know that tau is 2 minutes or 120 seconds, and we want to know how much time it takes to get the amplitude at that time equal to half of the original value. Right. All right. This time, whenever we're dealing with exponential decreases, this sort of time we always refer to as the half-life. How long does it take for that exponentially decreasing number to decrease all the way to half of what it had been? So again, the way to do it is to start by using that exponential equation for amplitude and inserting everything we know. So we're looking for a time at which amplitude is half of what it was at the start, but amplitude at any time is amplitude at the start e to the minus time over tau, but we know what tau is in this case. It's 120 seconds. 120. So again, we simplify things by canceling out these a zeros on both sides of the equation, and what do we have? One half equals e to the minus time, which is the length of time it takes for the amplitude to get down to 1/2 of its original size, 120 seconds. Remember, 120 seconds is the time constant. That's how long it takes for the amplitude to fade away to 37% of its original size. So the time it takes for the amplitude to decrease to half is going to be a shorter time than that. Let's see how much shorter. By doing the same kind of thing. Compare this with the basic equation. 1/2 corresponds to y, and x corresponds to this exponent minus t over 120 seconds. But if we have this exponential relationship, then we know that log of y is just equal to plain old x. So y in this case is 1/2. And x in this case, the exponent is minus t over 120. 120 seconds. So, in this case, minus t is log of 1/2. The minus sign here makes sense because the log of any number less than 1 is negative times 120 seconds. And that comes out to about 83 seconds, roughly 1 minute and 20 seconds. So you'll practice that a lot more in class. Not only in this case, but there'll be other situations coming up later in the semester where we'll think about exponential change again. The other idea that we wanted to introduce just a little bit right now is resonance. The basic idea of resonance is that you've got an oscillating system that you could either just let it go and watch it oscillate without any interference, Or you could continually, regularly, periodically interfere with it. You could give it a push every once in a while, which would be especially useful if there's friction taking away mechanical energy. Right? Anytime you give it a push, you'd be doing work on it. So that would be an opportunity to restore, give it back some of the mechanical energy that it had lost because of all that friction. Well, every oscillating system has a normal frequency at which it naturally likes to oscillate. In the case of our basic mass spring system, we've seen that the period time it takes to make one cycle is 1/2 mass, is 2 pi times square root of mass over k. Frequency is just the inverse of the period. This is seconds per cycle, and frequency is the number of cycles you get per second. So that's 1 over 2 pi times square root of k over m, just the inverse of our period equation. That's the frequency at which the system would oscillate if you just pull the mass to one side and then let go and just not interfere anymore, just watch what happens. That's we call the natural frequency. On the other hand, if I wanted to keep this system going and not let friction damp the oscillations down to 0 amplitude, I give it a push every once in a while. And I can push at any frequency I choose. The frequency of the outside force that does that pushing we call the driving frequency. Now, resonance happens when the driving frequency takes on a particular value. Depending on the driving frequency, like the frequency of my pushes in this case, the oscillations have different amplitudes. If the driving frequency gets close to the natural frequency, you get big amplitudes. And the farther away the driving frequency gets from the natural frequency, the smaller the amplitudes. That's the basic idea behind resonance. Resonance just means pushing on the system to keep it going and pushing at a frequency right at or close to the natural frequency. So why does this work? Why does pushing at the natural frequency give you the big amplitude? Well, remember the connection. Amplitude squared and mechanical energy are proportional to each other. So in a situation like this where you're getting a higher amplitude, that's a sign that the system has more mechanical energy. Where did that mechanical energy come from? It came from the work that I did when I was pushing. So the mass is oscillating back and forth. And of course, once every cycle, it'll be passing through equilibrium and moving to the left. Let's say every time the mass is in this situation, I give it a leftward push. So I'm doing work on it. What kind of work am I doing? Well, remember the equation. Work is just the magnitude of my pushing force times the magnitude of the displacement that the mass goes through while I'm pushing, times cosine of the angle between the displacement and the push. But I'm pushing this way. Well, the mass is moving the same way. If the mass is moving that way, then its displacement points to the left also. In other words, in this case, the angle between my push direction and the displacement direction is no angle at all. They're pointing in the same direction. So you've got a cosine of 0, which gives us +1, which is the largest possible value cosine could have. But the significant part here is that that guarantee, cosine equal +1, guarantees that the work is positive. Positive work means energy is given to the thing that feels the force. Well, if I push every time the mass is right here, passing through equilibrium going this way, that means I'm pushing once per cycle. In other words, the frequency of my pushes is the same as the natural frequency. And by doing that, I guarantee that every time I push, my push will be in the same direction as the displacement. So that guarantees that every time I push, I'm doing positive work. In other words, every time I push, I'm giving more energy to the system. On the other hand, if I pushed at a frequency that was different from the natural frequency, sometimes I'd be pushing this way when the mass was actually moving this way, and that would give positive work. I'd be adding energy to the system. But at other times, I'd be pushing this way while the mass was moving the opposite way. So in those cases, say if the mass is moving this way, it's got a displacement to the right, but I'm pushing to the left, then in that case the angle between the displacement direction and the force direction, they're directly opposite to each other. The angle is 180 degrees. And so in that case, the work done is just the strength of the push, magnitude of the displacement that happens while I'm pushing, times cosine of that angle, 180 degrees. As we've seen earlier, cosine of 180 degrees is -1. So that means, with this factor being negative, the work done is negative. So in that case, my push would be doing negative work. My push would be taking energy away from the mass. That's kind of obvious, because since the mass is moving this way, if I push backwards on it, it's going to slow down, so its kinetic energy will be decreased. I will have taken away some of its kinetic energy. So in other words, if my driving frequency, the pushing frequency, is significantly different from the natural frequency, then that means that only sometimes will I be pushing the correct way to do positive work and add energy. And it also means that sometimes I'll be pushing precisely the wrong way to give it energy. I'll be pushing in such a way as that I do negative work and take energy away. So that's why resonance happens. If you push at just the right frequency, then you're guaranteed that every push will do positive work and keep on adding and adding more and more energy. But if you push at a different frequency, sometimes you'll do positive work and add energy. Sometimes you'll do negative work and take away energy. That's the basic idea. So we'll look at more examples of that in class. But here's just one example. Let's say a little kid is on the swing, and the rope that connects the seat of the swing to the pivot point of the swing is 2 meters long. The length of the swing is 2 meters, and I want to be able to push on that kid so as to maximize the amount of energy that I give to that oscillating kid. And by maximizing the amount of energy that I give, I maximize the mechanical energy, to be specific, and that maximizes the amplitude, makes the kid swing back and forth farther at bigger angles. So obviously I want to push at the natural frequency. The natural frequency is the frequency I want to push at. What is the natural frequency? Well, a swing is essentially a pendulum, and we learned that in reading through the text, we learned that the natural frequency for a pendulum is 1/2 pi g gravitational acceleration 9.8 over length of the pendulum, length of the swing in this case. Period is just the inverse of that. So the natural period of the pendulum is 2 pi L over acceleration due to gravity. So in this case, we've got 2 pi square root of 2 meters over acceleration due to gravity 9.8 meters per second. And when you do the numbers, then you find that the natural period for the kid on the swing is 2.8 seconds. If I just left the kid alone to swing back and forth, the kid would go through one cycle in 2.8 seconds. So I need to push every 2.8 seconds in order to maximize the amount of energy that I give to the kid and that will maximize the amplitude of the kid's swing.